Hello and welcome to another video. In this video we're going to be working on a median of two sorted arrays. And I will start by saying this problem is very unintuitive to get, but I think we're going to be able to work it out and kind of give you some intuition on how to do it. And then from there, what I would definitely recommend is once you get the intuition, like once I draw the pictures, I would definitely recommend doing the problem yourself before seeing the solution. But let's get started. So you're given two sorted arrays, nums1 and nums2 of size m and n, and you want to return the median of the two sorted arrays. And the overall time complexity should be O of log m plus n. So in this first one you have 1, 3, 2. So essentially if you get a median, they're basically saying like combine these together, and what's the median? So if you combine these together in a sorted order, it would be 1, 2, 3. And the median, remember, is just the middle number, right? So it would be 2. And then similarly here we have 1, 2, and 3, 4. So if we combine those together, so the median of an even array is just going to be the mean of the two numbers in the middle. So you take these two numbers in the middle and you get their mean, and that's 2.5. And so the problem with this problem is like it would be very easy, or maybe not very easy, but it would definitely not be a hard problem if you could like merge sort these, or not even merge sort, if you can combine these arrays, right? Like if you could just take 1, 2, and 3, 4, and you can just say, okay, let me just combine those into one array, right? Like loop through them, combine them, they're already sorted. You don't even need to do a merge sort, just a normal like walk through them, find which number is smaller, and so on. The problem though is that would be m plus n time complexity. So that's going to be too slow. But yeah, if you could do that, that would be an easy problem. Or not an easy, but easy to medium. But the problem is you can't. You need to be able to do it faster. And so we're going to actually find the median without actually combining these two arrays, and it's definitely tricky. So let's just get an example here of two arrays, and we're going to go through two examples, and we're going to figure out like what we actually do. So let's get two examples. So the first example will just be an array of 1, 2, 3, 4, 5, 6, 7, 8. And the second example will be of 1, 2, 3, 4. So what we're going to do is we're going to figure out, first thing, how many total items are there, right? And we can just say that's like t or something, or total. So the total items, that's pretty straightforward. You just combine the length, so it'd be 12. Then we want to figure out what the half of that is. Also pretty straightforward. It's going to be 6. So then what we need to do is we need to actually, and you can do this through either one, but we're going to choose to binary search through the smaller array. You could do either one, but you can just say like, let's say this is, nums1 and this is nums2. If it's the other order, you can just reverse them. Because you have to binary search through one of them, and so it's going to be faster to obviously to binary search through the smaller one. Because then your time complexity will be log of the minimum of m plus n instead of the, whatever random one. So essentially, if you think about it, we have to split our array here into two parts. The part that comes before the median, or like the left part, and then the part that comes after the median. And so let's figure out what that's going to be, essentially. So here we have a half is 6. So that 6 has to be some part of this array and some part of this array. So for example, let's say I chose to pick this part, right? Let's just say randomly I chose to pick this part is before and this part is after. Then we're going to try to split it as evenly as possible. So if we have 2 and 2, we're going to have to split this into 4 and 4. So essentially, this part and this part need to come before this part and this part. And we can verify that by making sure that all of these numbers are less than all of these numbers, right? So clearly, this wouldn't be a good split because this 4 is actually, greater than this 3, so this wouldn't be a good split. But that's kind of an example. Once you figure out one possible split for this one, you can figure out the rest, right? Like once you figure out possible split here, let's say you're going to use 2 elements. That means you have to use 4 elements for the second one to get that split before the median. So essentially, we're just going to binary search through possible splits, and there's going to be like a way to tell if our split is correct or if our split is incorrect. And essentially, we're going to use the midpoint to figure out where our split is. And because we're going to binary search, it's going to be pretty fast. And so our midpoint is going to represent the last number in the left part of the split. And so it can be any index. Actually, it can also be outside of the array. So our midpoint here can actually be outside, which means our left side has nothing, right? And our right side has this. So then to have an even split, then our left side here would have to have 6 elements, and our right side would have to have 2, right? So we have 6 and 0 and 4 and 2, which would be like a split. Would it be a good split? Obviously not, because you can see that like this has to come before this, but we'll get into that. But that's possible, right? So the midpoint can be anywhere from 1 out of bounds to here. Any one of these is valid. So essentially, we're just gonna pick our midpoint and kind of see what happens, and we're gonna walk through this. So let's say we pick this midpoint, right? Just the middle number right over here. That means our split will be, this is gonna be the left side, right? This section is gonna be the left side. So, and now we need to figure out what's gonna be like the last number in the left side of the top. So if there's 2 numbers in the left side here, remember we need 6 per half. That means there need to be 4 numbers in the left side here, so we can just take this value. Right, so we can easily, from this value, we can easily get this value, we can easily get this value, and we can easily get this value. And I'm actually going to show those in different colors because that's going to be important. So the green is going to be the end of the left side, and then the brown is going to be the start of the right side. So it's going to be like this. And now, how do we check for a valid split? Well, that part is pretty straightforward because they're sorted. This number has to be less than or equal to this number, and in which case it is. And this number has to be less than or equal to this number. And here it's clearly not, right? So this 4 is greater than this 3, which means we would want to include the 3 instead of the 4, right? Like we're gonna want to have a split here that is going to include the 3 instead of the 4. We don't know exactly how many numbers, but we know this needs to be longer. Like our split right now is this, and we know our split needs to be longer. So we're going to say, okay, this is not a valid midpoint, so let's actually move our right now to be, or sorry, our left to be over here. Because this was not a valid midpoint, we need this part to be longer. So now there is a midpoint somewhere here, and there's always going to be a valid midpoint. But now we kind of do the same thing. We're going to say, okay, we're going to try one of these. And so let's just try this one over here as our left, which means we have 3 numbers here, so we have to have 3 numbers here, so we're going to put that over here. And then our right side will be this and this. It's just the number after. Now we can check again. So we can check, okay, so this 3 has to come before the 4. It does. And this 3 has to come before the 4. It does as well. So these numbers are actually the first 6 numbers that have to be in the array. And that makes sense, right? We have 1, 2, 3, and 1, 2, 3, which makes sense because 1, 2, 3, and 1, 2, 3 have to come before the rest of this whole thing. So we have like a valid solution now. And then once you have a valid solution, now we need to figure out what's the median. And there's going to be 2 cases here, and we're going to go through both of them. But essentially, in this case, remember we have an even number. So to get the median of an even number, what you have to do is figure out like when you add these 2 arrays, they're going to be combined into one, right? And the biggest number in that left side is going to be either this number or this number. So we need to get the bigger number out of these 2, and that's going to be like our left side, right? Whatever the bigger number is here is going to be our left side. So we can say like the max of these 2. In this case, they're the same. It's just going to be 3. Similarly, on the right side, they're going to be our right array, right? So if you have a left array of a bunch of numbers and you have a right array of a bunch of numbers, and they're equal size, the median is the biggest number here and the smallest number here added together divided by 2. So that's kind of what we're doing here. We're essentially getting the biggest number on the left side, which is the bigger number out of these 2, and the smaller number out of these 2. In this case, they're both 4, but if they weren't, we would take the smaller number, we would add them together, and we would divide by 2, and that would be our median. So it'd be 3.5, right? And that's how you calculate a median on an even number array, because there is no midpoint. The median represents a midpoint, but there is no midpoint. And let's just say we drew this sorted. Let's see what that would look like, right? Just to make sure we have what we wanted. So if we had 1, 2, 3, 4, 1, 2, 3, 4, and we actually combine those, so it would be 1, 1, 2, right? 3, or it would be 1, 1, 2, 2, 3, 3, 4, 4, and then it would be 5, 6, 7, 8, like this. And so this is length 12. So we would take the 6th number and the 7th number and then get their average, which would be 3.5. So that is correct. So that's essentially what you do, is you just check, you just set some kind of like starting point for your left and your right, and then you can always check is my left array too big or too small, or just the right number, right? And like I said, in order for it just to be the right thing, this number has to be less than or equal to this number, and this number has to be less than or equal to this number. And if one of these isn't true, then you just move this midpoint accordingly, and then you'll eventually get a midpoint. So we did this with a even number array. Now let's try an odd number array. So we'll just add a 5 here for simplicity, and let's just redo all of this. In fact, we can even make it harder, right? Instead of adding a 5, let's add like a 9 or something, right? There we go. Okay. And so as long as they're both sorted, it will work. So let's just go through our algorithm again. So for our total, we have 8 numbers and 5 numbers, so we have 13. So for the half, for the left half, we're always going to want to have, if it's an odd number, we're always going to want to have total over 2, but lower divided. So we're going to want to have 6 here. Yeah, we're going to want to have 6 on the left side, and then it's going to be easier to get the median. So let's do that. So remember, our right pointer is over here, and our left pointer can technically be out of bounds because technically the left side can be an empty array and the right side can be this whole thing, right? That's totally fine. That is a possibility, which would mean that this whole array comes before this whole array, which is totally possible, right? Like this can be 1, 2, 3, 4, 5, 6, 7, 8, and then this can be like 9, 10, 11, 12, and so on. And so this whole array would need to come before this whole array. Also, what we need to do in our actual problem is we need to represent, like we can be out of bounds in both of these. And so the way we're going to do this is represent left by negative infinity. If we're out of bounds on the left side, we're going to make that negative infinity. And if we're out of bounds on the right side, we're going to make that positive infinity. Which makes a lot of sense, because let's say this whole array needs to come before this whole array, then this left should be negative infinity, right? Because then you have negative infinity, and then you have this whole array, which makes sense, right? That would be in the right order. Then you would have this whole array. Similarly, if you had it the other way, like let's say in this case, this whole array needed to come before this whole array, right? Like this was 1, 2, 3, 4, 5, then we had 6, 7, 8, 9, 10, and so on. So 1, 2, 3, 4, 5 would be here, and then our midpoint would be here, and then our right side would be infinity, which would also make sense because it would be this left side, right? We'll call that left. Then this thing, right? Then this whole thing, so right, and then infinity is going to come afterwards, which makes sense, right? So that's the way we're gonna represent being out of bounds. But anyway, let's go through this. So we're going to have a right here, we're going to have a left here, and we are going to get a midpoint once again. So our midpoint on this will be over here, right? Because essentially our midpoint will be the middle of these two, which will be, we always lower divide, so it's going to be, and we want to get the smaller, right? We always want to like divide it smaller. Okay, so if our midpoint is here, we have 2 numbers here. That means we need to have 4 numbers here, right? Because we need to have 6 numbers on the left side. So if we have 4 numbers here, our end of the left will be here, and these are very easy to calculate, right? Like if you know this index, you can get this index just by a simple math calculation. You can get it in O of 1 because you know exactly how many numbers you need. So then similarly, our right side will be here and here, and now we are going to check, is their stuff fine? So remember, this 2 needs to be smaller than the 5. It is, right? This is fine, but this 4 is greater than the 3. Which is a problem. So this 3 needs to be included before this 4. So that means this was our left side, but it was too small. It needs to be bigger, right? So if it needs to be bigger, we're going to reassign our left and our right, or our right is going to stay the same, but our left will move over here, right? Like this left side needs to be bigger. And then we're going to do this again. So we are going to say, okay, what's the midpoint here? The midpoint is right over here. So how many numbers do we have? 4. That means we need to have 2 in this side. So we're going to have 2 in this side. And then we're going to have the right side and the right side, and we're going to compare again. Okay, so we can check if we met our criteria, right? So this left thing needs to be smaller than this right thing, and it is, right? 2 is smaller than 9. But this left thing needs to be smaller than this right thing, and it's not. So this 4 is too big. So this 4 is included in our left side, right? If we drew our left arrays here, it would be this one and this one. But as you can see, we included this 4 and we didn't include this 3. So now our array is too big on this side. So if our array is too big, we need to make it smaller, this left array. So what we need to do to make it smaller is pretty straightforward. We're going to need to make the right over here now, right? Just from like a binary search. Now our midpoint will be this value, and let's figure out what we need on the right, what we need on the top. So we have 3 values here, so we need 3 values here. Now let's try it, and this should work because this is the only number we have left, so hopefully it does. So now this is the right side and this is the right side. Now let's check. Is 3 less than 4? Yes. Right? And is 3 less than 4? Yes. And if you think about it, this would be our ideal split, right? Like our ideal split would be just like this. It would literally be 1, 1, 2, 2, 3, 3, 4, 4, 5, 6, 7, 8, 9. And so if you took the left side of that, it would be 6 numbers. So these 6 numbers right here, which are the same as these 6 numbers right here. So it is the same, and now our right side would be this, and our median would be the middle number. So let's go over how to get the median when you have an odd number array, right? So you have 13 numbers, you have 6 on the left and 6 on the right. So this median is guaranteed to be one of these 2 numbers, right? Because you have the left and you have the right. But which one is it? Well, if you think about it, right, this is increasing. So it's going to be the smaller one of these 2 numbers is going to be the median. Once again, they're equal, but if they're not, it would be the smaller one. Like if this was a 4 and a 9 or something, you would take the smaller one because the median is going to be the number that's right after the biggest number here, right? Right after, which means the smaller one of these. So in this case, we would return 4, which would make sense. So now we kind of have everything we need to be doing. We are essentially binary searching through the smaller array, getting some kind of like left side, and then from that we're getting the left side for the top array just because they have to add up to some half. And then we are simply checking, is this green thing smaller than this brown thing? And is this green thing smaller than this brown thing? Which means our arrays are partitioned perfectly. And if not, we just update our pointers accordingly until we're out of bounds and we're guaranteed to have an answer. And the answer might include not using any part of this array or using this whole array, but that's going to be in our bounds. So now we have enough to code it up, and it's going to be a decent amount of code. So let's go through that. So first, what I'm actually going to do is I'm just going to rename these to X and Y just to make it a little easier, because I'm going to reuse these variables a lot, and it's going to be kind of hefty amount of code. So the first thing I'm going to say is if length of X is greater than length of Y, I'm just going to swap them. And this is an O1 operation in Python because you're not actually like moving elements around, you're just changing pointers. You could also, instead of swapping them, you could also just call this function again and pass in the arguments backwards, right? So you could call this on YX and that would work too. Because essentially you want X to be smaller because we want to binary search through the smaller array because that's going to be faster. Now we're going to make our left and our right for the binary search. So like I said, it can be out of bounds or length of X minus 1 could be the final index. Now we're going to make a total, also pretty straightforward. So length of X plus length of Y. And then we're going to make a half. That's going to be total lower divided by 2. Now we are going to just do a normal binary search. We're guaranteed to have an answer because our bounds are correct. Now we need to get 2 pivots essentially. So first we're going to get like a normal pivot. So we can call this pivot X equals left plus right plus, or lower divided by 2. But now we need to get a pivot Y, and this is going to symbolize, I'm going to go back to this picture a lot, this is going to symbolize this green arrow on the top array, right? We got the pivot for this one, but we need to figure out what it is for this other one. And the way that's going to be is, it's actually going to be half, right? However many elements you have, minus pivot X. And then you also have to subtract 2 because arrays are 0 indexed, right? So in order to actually get the right index, because they're both 0 indexed, you have to subtract 2. And you can work out the math. You can just do some examples. Like if you do some example here, like if this is the number here and the half is some number, what index should this be? And you can kind of see that and figure it out. But yeah, essentially because they're 0 indexed and there's 2 of them, you have to subtract 2. Now we are essentially going to break this code down into the right side and the left side like I showed. So the left is going to be the rightmost value in the left side, right? Just like I showed you in this picture. The left is going to be the rightmost value in the left half, and the right is going to be the leftmost value in the right half. And so we're going to do that. So we're going to say, we can do the right side maybe first, or we could do the left. Like either one's fine. I think let's just do the left side first maybe. So we could say left X equals, it's going to be X and then pivot X if pivot X is greater than or equal to 0. Otherwise, remember, if we're out of bounds, we're just going to initialize that to negative infinity. Similarly, for the right side, we're going to say right X equals X pivot X plus 1, right, the one right after it, if pivot X plus 1 is less than length x. Otherwise, we're out of bounds again, so we'll make that infinity. So we'll float infinity here. And then we do the same thing for the y. So we're going to say left y equals y, pivot y. If pivot y is greater than or equal to 0, else float negative infinity. And the same thing for the right y. It's going to be y, pivot y plus 1. If pivot y plus 1 is less than length y, else float infinity. So literally the same thing. Hopefully I don't screw up anything here. So now we have to essentially check if our stuff is correct, right? Like if all our logic is correct. So what we have to do is we have to say, okay, if left x, so remember, going back to the picture, so the left x is going to be this bottom one. This green has to be less than this brown, right? So this is left x, this is right y, and similarly left y has to be less than right x. So we have to check for both of those. So if left x is less than or equal to right y, and left y is less than or equal to right x, then we have to check, do we have a even or odd number for the median? Because you're going to calculate a different area. Is there total odd or even? So we could say if total mod 2, right, if it's odd, let's do that first. And so that one is going to be return min of left x and right y. Or actually, it's going to be left x and left y, right? So it's going to be min of left x and is that right? Actually, no. It's going to be the right one. Yeah. So right x and right y, right? Going back to this picture, so this was actually a this was an odd number. So you're going to take the two right sides and you're going to get the minimum number there. Yeah. Okay. Otherwise, it's a little trickier. You're going to return the maximum of the left side, so left x, left y, plus the minimum of the right side, so right x, right y. You're going to get both of those, and you're going to divide by 2, and it's not going to be an integer divide, it's going to be a floating point divide. And so that'll take care of both of those. Now we have to check for our two cases, essentially, right? So we can check for one of these, so we can just check, like, if right x is greater than left y. Let's see what the, actually, we want it the other way, though, so we want it left x is greater than right y. So let's kind of look at the picture to show where we should be going. So if this left is greater than one of these, that means we are including too many numbers here, right? That means that, like, if this is greater, that means that, like, let's say we're including this whole thing, and then the number we're comparing to is this, that means this is too big. So if it's too big, we're going to want to make it smaller. So how do we make it smaller? That's going to be right equals pivot minus 1. And then otherwise, we're going to want to make it bigger. So else left equals pivot plus 1. And we shouldn't have to return a default value, and I would be highly shocked if this worked without any errors, but let's see. So I do need to actually get rid of this. I can see some stuff here. Let's take a look. Oh yeah, so this needs to be pivot x and pivot x. Yeah, see what happens. If that's, okay, nice. And so this is pretty much as efficient as you can get with this problem. Like, yeah, you basically, it's all over the place. But essentially, it's as efficient as you can get with this problem. So let's actually go through the time and space now. Let's actually minimize this. And let's do that. So for the time, let's kind of look to see what we're doing. So essentially what we're doing is this part is O of 1, this part is all O of 1. This binary search is essentially looking through the smaller array, right? If you have like M and N, it's looking through the smaller one, and it's doing a binary search, and all of these are O of 1, like this is all O of 1, this is all O of 1, this is all O of 1. So essentially every single operation here is O of 1. So this would just be O of the log of the minimum of M and N, because we're essentially saying, let's just binary search through the smaller array, right? And if we have the big array, we can just swap them. And so for the space, we have some variables, but we never actually declared, we never actually made it a new array. We have a ton of constant variables, we never made a new array, so it's actually going to be a 1. But yeah, I think this problem is quite tough, especially, I would say it's very tough to like get started. And then once you get started, it's still not easy to code, so I definitely recommend, at least for me, even once I saw the solution to this one, I still kind of like forgot it in a while, so I definitely recommend to either code it up before you see the solution, like once you kind of get the intuition, or save this one and try to code it up in like a week or two when you don't remember the exact solution. Because there's still like a lot of edge cases, and it's not very intuitive. And it's definitely a good one to practice. And I'm not a huge fan of this problem because it doesn't really use like an algorithm, it's very unintuitive, like it's just kind of weird. It's like you have to get the intuition for it, but it's definitely and like I said, even if you know kind of what you're doing, it's still not that easy to code, right? There's a ton of edge cases. There's all these like out of bounds errors. So I would definitely strongly recommend to code this one up again. I think this is one of the harder ones to, even if you see a solution, to remember and to code up on your own. But yeah, it's going to be it for this problem. Hopefully you enjoyed it. And if you did, also, by the way, so the other thing is, this is a really common interview question, apparently. This is like in the top 20 interview questions. So if you are going to be interviewing, strongly recommend to know this one, especially for like the harder problems. Definitely strongly recommend to know this one. But yeah, it's going to be it for this one. And if you liked it, please like the video and subscribe to the channel. And I'll see you in the next one. Thanks for watching.